Welcome back to the Deep Dive. This is the place where we ditch the dense technical manuals, all the compliance boilerplate, and we really take these crucial architecture decisions and distill them down into something you can use.
Into actionable knowledge.
Exactly. And today we're doing a deep dive into Google Cloud Storage. Now, this isn't just about, finding a home for your files.
Not at all.
It's about mastering the architecture underneath it all. Things like immutability, location, automation, all to manage, potentially, petabytes of data all over the world.
And, critically, to secure your most sensitive assets and avoid that catastrophic cloud bill at the end of the month.
That's the big one.
That's our mission today. We're taking those architecture documents, the ones that define where your critical data lives and how it moves, and we're turning them into simple, efficient strategies. Cloud storage is one of the most fundamental services in GCP.
And one of the most used, for sure.
Heavily used, and yet the most common errors we see really stem from misunderstanding its core structure. It's just not traditional.
Right. When most people think about storage, they immediately map it to what they know, like a server file system. Hierarchical folders, directories, files you can just modify in place.
And cloud storage just completely rejects that model.
It's all object-based.
Precisely. The shift is away from that hierarchy, forget inodes and file tables, and it's all about objects within buckets. It's a flat namespace where everything is an immutable object.
And that design is what lets it handle that massive scale, right? From a single byte up to
multi-petabyte volumes, all retrievable instantly with a simple HTTP request from anywhere in the world.
Okay, so here's where the technical foundation really differentiates GCP. We often hear about how other cloud storage solutions can have issues with data sync, with what's called eventual consistency. But cloud storage operates under a standard of strong consistency. What does that actually mean for the person building an application or managing critical data?
Strong consistency is, it's the non-negotiable bedrock of reliability here. It means there is no lag time. There's no ambiguity, no uncertainty about the state of your data.
So no waiting.
Zero waiting. If you upload a new object, or you update its metadata, or even just list the contents of a bucket, that change is guaranteed to be immediately and universally visible to every single request after it, globally.
Right.
There is zero window where you might accidentally download an old version or see a file missing from a list. For, highly transactional systems, financial reporting, anything that demands that immediate read-after-write reliability, strong consistency, is mandatory. It's not a luxury.
So we're framing this deep dive as the essential knowledge you need to go from just, using cloud storage to architecting it strategically.
Exactly. Mastering buckets, storage classes, lifecycle automation. That's what separates the people who control their infrastructure from the ones who are controlled by it.
And by their spending.
So let's start at the foundational level. The mandatory container, the cloud storage bucket.
Every single piece of data, every object, has to live inside a bucket. The bucket is that foundational piece that dictates, everything that comes after.
Everything. Security policies, the physical location of the data, and the cost structure.
And that brings us immediately to the first, huge architectural constraint.
The global constraint, yes. Cloud storage buckets are defined as global resources. And this has enormous implications, especially for naming.
Meaning?
Every bucket name must be globally unique across all of Google Cloud, across every project, every region, worldwide. If company alpha customer invoices is taken by some competitor in Asia,
you can't use it.
You can't use it in North America, even in a totally separate GCP project. It's gone.
That global competition for names must mean the naming rules are incredibly specific just to maintain some order. What are the rules we need to warn our listeners about?
Oh, they are rigid, and they're unforgiving. Names have to be between 3 and 63 characters long, and you're strictly limited to lowercase letters, numbers, hyphens, underscores, and dots.
That lowercase only rule is a big one. It trips up a lot of developers who are used to, Path-cow case or camel case for readability.
It does, and the exclusions are just as critical, especially for security.
Right. I remember seeing a long list of forbidden terms.
The crucial exceptions are there to prevent impersonation or system confusion. You absolutely cannot include the strings Google or GCP or anything that looks like a misspelling of them.
Can't start with Goog either, right?
Cannot start with Goog, and the name can't resemble an IP address. These rules are there because the bucket name is often used in URLs and DNS, so you have to avoid any ambiguity with official Google domains or network IDs.
The source material also flagged dots. They're technically allowed, but generally discouraged. Why is that? If they're a permitted character, why should we avoid them?
It's a pragmatic choice, really, and it's all about web serving. If you plan to serve content directly out of your bucket-like images for a website, and you want to use a custom domain, having dots in the bucket name can cause major headaches.
With DNS and SSL certificates.
Exactly. When you try to secure that endpoint with an SSL/TLS certificate, it gets complicated. So unless your app strictly needs dots for some domain mapping reason, just avoiding them will simplify your life and prevent security issues later.
Okay, so we have this globally unique, strictly named container. But let's challenge this idea of simplicity. Is it ever okay for a big company to just dump everything? Logs, images, backups, compliance records, all into one giant bucket.
That is a recipe for cost overruns and security chaos. The moment you decide to use one container for everything, you're forced into a single monolithic policy for everything.
So the ideal solution is what?
The multi-bucket strategy. You absolutely need a distinct bucket for every type of data that has unique requirements for cost, access pattern, retention, or location.
Walk us through that. Use a real scenario. Why does separating this stuff save money and headaches?
Okay, let's take that e-commerce platform we talked about. If you put everything in one bucket, let's call it e-commerce global data, you might decide it needs to be standard storage because your product images are accessed a lot.
And multi-region for high availability.
Right. But now, your infrequently accessed customer invoices, which you're legally required to keep but only touch once a year, they are suddenly sitting in the most expensive storage class, in the most expensive location.
Which is just terrible cost management. So how does separating it fix this?
You separate by function and by policy. You'd have e-commerce product images of us, and that's standard storage because it's hot data accessed constantly.
Yeah.
Then you'd have e-commerce customer invoices that could be nearline storage because it's cool data, rarely accessed. And maybe you'd make it regional in the EU for GDPR compliance.
And the logs.
E-commerce website logs global. That could be archive storage. Historical logs are the coldest data you have. You only need them for an audit once a year. This strategy ensures your access controls are tight where they need to be, like for invoices, maybe looser for public images, and your storage cost perfectly matches the access frequency of the data.
That separation leads us right into the next big choice. Location. The physical placement of the bucket dictates cost, latency, and resilience. And there are 3 tiers, right? Starting with the highest performance for local apps.
That would be the regional location. For example, US Central 1. The data is redundantly stored across multiple availability zones, but all within that single geographic region.
And that gives you the lowest cost and lowest latency.
Exactly. If your compute engine instances or your Kubernetes cluster are also in US Central 1, keeping the data in the same region is key. It minimizes network transfer time and maximizes speed.
What about the cost benefits? I hear about egress charges a lot.
That's a massive financial insight. Data transfer within the same region is usually free or very, very cheap. The traffic stays on Google's backbone.
But if your app is in, say, US West 1 and your data is in US Central 1,
you immediately start paying substantial network egress charges every time that app has to pull data across that boundary. So for cost-conscious, single-region apps, regional storage is the default choice.
okay, but what if we need a big step up in resilience, in availability?
Then you move to dual region.
Like NEM4.
Right, like NEM4, which spans 2 distinct regions, like US Central 1 and US East 1. Your data is redundantly stored across both of them. It costs more, for sure, but the benefit is huge. Disaster recovery.
So if an entire region goes down,
If a major disaster wipes out US Central 1, your application fails over, and your data is immediately accessible from US East 1. This is absolutely non-negotiable for mission-critical apps. Think payment processors or compliance reporting systems.
and if the goal is truly global access or just maximum reach, we go for the top tier.
Multi-region. It's just named US or Asia or EU. It gives you the highest degree of geo-redundancy. Your data is stored across at least 2 geographic regions within that huge area.
So that's for global apps, big data analytics, or serving as an origin for a CDN.
Exactly. It's the top tier for availability, guaranteeing quick retrieval no matter where your user is in the world.
But the trade-off is significant, isn't it? You pay a premium for that availability, and you might lose that razor-sharp latency for a specific user.
Absolutely. Multi-region has the highest storage cost. And while the average global latency is great, the latency for any single request might be a tiny bit higher than regional storage, just because the routing layer has to figure out which location is the fastest source for that specific request. It's a strategic choice. Are you optimizing for cost and latency in one region or for maximum global resilience?
All right, let's move from the container to the content itself. The cloud storage object, this is the actual payload, right? The immutable piece of data.
Right. It could be a tiny config file or a massive 5 terabyte video asset. That's the max size for a single object.
And you said the key word there, immutable.
Immutability is fundamental to understanding the durability and consistency guarantees of cloud storage. Once an object's content is stored, it cannot be modified in place.
Okay, let me push back on that for a second.
Sure.
As a developer, if I upload a document and then I realize I misspelled a word, I can open it, edit it, save it back to the bucket. It feels like I modified it. What's really happening?
What you're experiencing is it's an illusion of modification. When you hit save, you're actually making a whole new API call that does an overwrite operation.
So I'm not editing, I'm replacing.
You are replacing the original object entirely with a new version, a new payload. It simplifies data integrity immensely because the system never has to worry about partial writes or complex locking. If you want to change an object, you replace the whole thing.
And this idea relates directly to the biggest conceptual hurdle for newcomers, the flat namespace illusion. When I look at my bucket in the web console, I see folders. I see invoices 2024 Q3 customerx.pdf that looks and feels exactly like a file system.
It's a necessary abstraction layer, but just for us humans to read it. Cloud storage is a pure, flat namespace. When you name an object invoices 2024 Q3 customerx.pdf, that entire string slashes and all is just the object's unique key.
A single identifier.
A single identifier. There is no 2024 folder that contains a Q3 folder. It doesn't exist.
Why is that distinction so important from a technical standpoint?
Because it makes indexing and retrieval incredibly fast. In a traditional file system, to get a deeply nested file, the system has to traverse the hierarchy. It looks at the root, finds the invoices directory, then 2024, and so on. Multiple lookups.
But in cloud storage,
In cloud storage, the system just looks up the entire key string, that flat address, in a massive distributed index. That design choice is what allows it to handle billions of objects with near instantaneous retrieval times, no matter how deep your artificial folder structure looks.
okay, moving beyond the data itself, there's the object's crucial descriptive information. Metadata.
Right. This is what turns, opaque bytes into useful, searchable business assets. Metadata is the context.
And we break it into two types.
We do. First, there's the system-defined metadata. The system manages this automatically when you upload or create something.
What are the must-know fields there?
Well, the basics include content type, which tells a browser how to handle the data, text plain or video 4. You have content length, the size, and crucially, the CRC32C checksum.
The integrity check.
It's your guarantee of data integrity. This checksum is calculated on upload and it's verified on download. It's your technical proof that the object you got back is byte for byte identical to the one you uploaded. It protects against transit errors, bit rot, everything.
And then there's custom metadata, which is where we inject our own business logic. This is arguably the more powerful tool for an architect.
Oh, absolutely. Custom metadata lets you attach your own key value pairs that travel with the object. You could tag objects with, say, creator, Jane Smith, department, finance, or maybe a retention date, 2028-06-01.
And that's transformative because you can then search and filter based on that.
And even drive automated lifecycle decisions based on business criteria, not just on file names or timestamps. It's incredibly powerful.
This leads us naturally to versioning. If replacing an object is an overwrite, how does versioning act as our safety net?
When you enable object versioning on a bucket, those overwrites or deletes don't actually destroy the old data. Instead, the older state is automatically kept as a previous version.
And each one gets a unique number.
Each one gets a unique, immutable generation number. This is a powerful hedge against user error or application bugs. It's your undo button.
So we have to be really clear about the different version types because that's critical for setting up cleanup policies later.
Correct. The live version is the current, most recent one. It's what you get by default when you access the object. All the previous states are called non-current versions.
And that distinction is key.
It's key because your lifecycle rules will often target only those non-current versions. You might say, delete all non-current versions after 90 days while keeping the single live version forever. Versioning is really the foundational insurance policy for any critical data.
Okay, now let's shift gears completely to the strategic financial side of things. Not all data is the same temperature, right? Some is accessed constantly, some is frozen in deep storage.
And storage classes are the mechanism that lets you match the cost of storage precisely to how often you access it.
It's a trade-off.
It's the essential trade-off. A lower monthly storage cost always comes with higher fees for retrieval and stricter minimum retention periods. But the great equalizer here is performance. All four major classes offer the same high first byte latency. The cost difference is all about your access pattern.
Let's break down the 4 tiers, starting with the most frequently accessed or hot data.
That's standard storage. This is for data you're hitting multiple times a day. It has the highest monthly storage cost, but it has the lowest operational cost and basically zero retrieval fees.
And no minimum duration.
Critically, no minimum storage duration. It's perfect for active user files, website assets, anything involved in heavy dynamic workloads where you need speed and flexibility.
Next, we move into data that's accessed, what, less than once a month?
Nearline storage. This is for your cool data. The monthly storage cost drops a lot compared to standard. However, you now have a moderate retrieval cost, and this is important, a 30-day minimum storage duration.
So this is good for things like nightly backups.
Perfect for nightly backups or logs you keep for a month of troubleshooting. You save money storing it, but you pay a small fee to pull it back out.
And the next level down is for data accessed maybe once a quarter.
That's cold line storage. For truly cold data, the storage cost is even lower, which makes it great for long-term retention. But the retrieval costs go up quite a bit, and the minimum duration jumps to 90 days.
So regulatory data, historical records.
Exactly. Data you have to keep for compliance, but only access during a quarterly audit or annual report.
And finally, the frozen in time, the Arctic storage.
Archive storage. This is for the coldest data you can imagine, accessed less than once a year. It has the absolute lowest monthly storage cost, but the retrieval and operation costs are the highest. And it mandates a very strict 365-day minimum storage duration.
So legal discovery documents, things you have to keep for decades.
Strictly for permanent archives, where access is extremely rare.
Okay, this brings us to what might be the most critical concept for anyone managing a cloud budget: the urge deletion trap. This is where the financial risk of choosing a cold class really hits home if you violate that minimum duration.
This is the financial gotcha. This is what catches people out. When you choose nearline, cold line, or archive, you're basically making a promise to the system that the data will stay there for that minimum period in exchange for the low rate.
And if you break that promise,
If you delete the object or overwrite it or, and this is a key one, move it to a warmer class before that time is up, you get charged an early deletion fee.
which is equivalent to what?
It's equivalent to the storage cost for the time that was remaining.
Okay, let's run the numbers on that to make it crystal clear. I upload a 100 gigabyte backup to cold line storage, which has a 90-day minimum. After 15 days, I realize it's corrupted and I delete it. What happens to my bill?
Okay, so you pay the standard storage cost for the 15 days the data was actually in cold line, but you immediately trigger the penalty for the remaining 75 days.
90 minus 15.
Right. You will be charged an early deletion fee that is equal to the cost of storing that 100 gigabytes in cold line for those 75 days, even though the data is gone. This is why mismanaging lifecycle policies on cold storage can completely wipe out any savings you thought you were getting.
You have to design your systems to let the data reach that minimum period.
You must.
So, manual lifecycle management requires knowing your data's access pattern with near-perfect accuracy. But what if you're dealing with, say, a huge legacy data lake migration? You have millions of files and zero idea how often they're accessed.
That unpredictable scenario is exactly why AutoClass was introduced. AutoClass is the simplified solution for messy data, for data lakes, or complex migrations where you just have no visibility into access patterns.
How does AutoClass change the game then?
It acts as a managed, automated intermediary. It monitors every object in the bucket. If an object is accessed, AutoClass moves it to standard storage for performance. If an object is left untouched for a while, it automatically transitions it to a colder class to save you money.
Now, I have to introduce some critical analysis here, because that sounds like the easy button. If AutoClass handles all the optimization, why would a mature architecture team spend hours creating manual, granular object lifecycle management rules? Doesn't AutoClass discourage that fine-grained optimization?
That's an excellent point, and it really defines the trade-off. AutoClass trades ultimate optimization for zero risk and convenience.
Also,
Well, AutoClass eliminates retrieval fees and it eliminates early dilution fees, two huge headaches. But it charges a small monthly management fee.
there's the catch.
So for a mature system with predictable patterns, like logs, manual rules will almost certainly be cheaper. But for that initial big migration or for a data lake where access is truly chaotic, that management fee is a small price to pay to guarantee you avoid a massive sudden retrieval bill when some old, cold object is unexpectedly accessed.
Which could wreck your budget otherwise.
It could bankrupt the cost model. It's risk mitigation, not maximum cost reduction.
Okay, so once we've figured out our multi-bucket strategy and storage classes, the next step is automating the whole process. And that's where Object Lifecycle Management, or OLM, comes in.
Right. This is how we ensure the system is constantly optimizing costs and meeting compliance without any human having to touch it.
So it's basically a policy engine.
It is. It runs on the bucket, evaluates a set of rules every day, and these rules just specify an action to take when a certain condition is met. It turns your policy into automated execution.
So what are the core actions OLM can perform?
There are three main ones. Delete, which is a permanent removal. Set storage class, which is the archival action, moving data from a warm class to a colder one. And a crucial cost-saving one, abort incomplete multi-part upload.
What does that do?
It cleans up partial uploads that might stall out, which prevents you from paying for fragmented, useless data forever.
And the conditions are where the real intelligence is. What defines when a rule kicks in?
The most common one is age, just measured in days since the object was created. For version buckets, we use days since non-current time, which lets us specifically target and clean up old versions while leaving the live one alone.
You can also do it by number of versions, right?
Yep, number of newer versions, like only keep the 3 most recent config files. And you can also match on storage class or live status to make your rules really specific.
Let's apply this to a real-world example like log files to show how aggressive you can be with cost optimization. Logs are generated, they're critical for maybe 24 hours, and then they're just compliance baggage.
A typical log file scenario, right? They hit the bucket as standard storage. Rule 1. Transition to nearline after 7 days. This gets the data out of the most expensive tier as soon as that immediate troubleshooting window is over. And we pick 7 days because it's well under nearline's 30-day minimum.
So you're respecting the minimum stay.
You are. Then, rule 2. Transition from nearline to cold line after 90 days. Now the logs are truly cold, just kept for a mandatory quarterly review, and we drop the storage cost even further.
And fine.
Rule 3. Delete objects after 365 days. This enforces a mandatory compliance deletion based on a 1-year retention rule, and it prevents those costs from piling up forever.
That's intelligent automation. It's not just saving money, it's an auditable, codified guarantee that your retention rules are being met.
Exactly. And moving from automation to guaranteed control, we enter the high-stakes world of advanced security. And the first critical feature here is Uniform Bucket Level Access, UBLA.
UBLA is the recommended default for new buckets now, but it's function disabling individual object controls. That seems counterintuitive. Why is taking away control a security improvement?
Because those individual controls, access control lists, or ACLs, they introduce immense complexity and massive risk at scale. When ACLs are enabled, developers can set permissions on millions of individual objects.
And one mistake can be catastrophic.
Imagine a misconfigured script or just one developer accidentally setting a public read ACL on a single object containing sensitive PII. That single object is instantly exposed to the world no matter how tight your IAM policies are at the project or bucket level.
So UBLA removes that weak point completely.
It forces consolidation and consistency. UBLA disables all ACLs for every object in the bucket. Access is then managed exclusively through IAM policies on the bucket itself.
So if you don't have the IAM role on the bucket, you can't read anything, period.
Exactly. It prevents those dangerous accidental granular exposures and makes security auditing way, way simpler. For any large organization, UBLA is non-negotiable.
The second feature is even more critical for regulation, the retention policy, or bucket lock. And this is different from a simple lifecycle delete rule.
Very different. The retention policy is specifically designed to enforce worm. Write once, read many. You define a fixed period, say 5 years, and during that time, objects in that bucket cannot be deleted or overwritten by anyone, regardless of their permissions.
It's legal-grade immutability.
It is, and the real power is when you use the locking mechanism. What happens when you lock the policy?
It's irreversible.
It is the irreversible step. Once that policy is locked, it becomes a permanent legal mandate. The retention period cannot be reduced or removed from the bucket. Not by the project owner, not by the org admin, not by anyone.
And that's what you need to satisfy regulations like SEC Rule 17A4.
That's the technical guarantee you need. It provides a chain of custody and proof of integrity that you just can't achieve with soft lifecycle rules that can't be changed.
That level of permanence really underscores the gravity of the decision. You're creating an unchangeable legal record inside your cloud infrastructure. Okay, we've covered the whole spectrum, from cost modeling to legal compliance. Let's integrate all these decisions back into our online learning platform case study to show how this multi-bucket strategy really works in practice.
Great idea. So we've got high-frequency content, sensitive student data, and necessary logs. This scenario demands 3 distinct policies.
Right, bucket 1, the content bucket, learning platform content. This holds all the active course materials, videos, slides, notes, needs fast access during the semester, but cheap long-term retention after.
Okay, so for that, we'd put it in a regional location, Central 1. The user base is regional, so that minimizes egress costs and latency for video streaming. Starts in standard storage.
But the critical cost optimization comes from the lifecycle rule.
Exactly. Transition to archive storage after 180 days. 6 months is plenty for the semester and grading. After that, we push it to the cheapest class possible to maximize savings on all that old video content.
Okay, bucket 2, the submissions bucket, student submissions. This holds graded projects, sensitive student work. Availability and retention are the top priorities here.
This is a high-stakes bucket. We'd start it in standard, but we'd mandate a dual-region location, name 4. The reason is compliance and academic integrity. Student records are sensitive. They need maximum resilience against a regional failure. The higher cost is justified.
And the retention has to align perfectly with the academic timeline.
It does. Rule 1, transition to cold line storage after 60 days. That 2-month window covers submission and grading, after which access is rare. We choose cold line with its 90-day minimum because we know we want to keep it longer anyway, and the cost is better.
And then rule 2.
Rule 2, delete after 365 days. This ensures data privacy and compliance by permanently purging that data 1 full academic year after it was submitted.
All right, bucket 3, the logs bucket. Platform analytics logs. This is that rapid cost reduction model in action.
Yep.
Regional location, us Central 1, to be close to the compute, starts in standard. Lifecycle Rule 1. Transition to nearline storage after just 1 day.
That is aggressive.
It's aggressive cost management. You get that critical 24-hour window for active monitoring, then immediately move the data to cheaper storage. And Rule 2. Delete after 90 days, which satisfies the common 3-month audit trail requirement without letting cheap storage just pile up forever.
That covers the high-level architecture. But for the pros listening, they need to know how these strategies translate into real-world operations using the command line tool, gstill.
Right, gstill is indispensable. It gives you that granular control for scripting. For instance, creating a bucket with a specific location and class, it requires explicit arguments that directly reflect our choices. Something like gstosil mbmb-c-l-lamem4gsl-students-submissions 2025.
And when you're dealing with that flat namespace, using gsutlcp really helps reinforce the concept. It does. When you upload a file with gsutlcp localasset.pdf, gs.bucketnamdocumentsconfidentialreport.pdf, you're confirming that that whole string, documentsconfidentialreport.pdf, is just part of the object's single flat key. There's no mkdir command involved.
And we talked about the power of custom metadata to attach business context. You could do that during the upload process itself.
You certainly can. Use the H flag to add HTTP headers that become metadata. For example, gsutlcph x-dugmetadepartment.marketingreport.xlsx gs.marketing-files.
And then you can see that metadata when you inspect the object.
Exactly. You run gsutl s-l and you'll see that x-gug-meta-department tag, proving that business context is traveling with the data, which helps with searching and governance later.
I think one of the most powerful advanced use cases is ensuring synchronization across systems, especially with massive change sets.
That's where recursive synchronization comes in. gsutul airsync-r is one of the most powerful commands. Instead of just copying everything, usync intelligently compares the source and destination and only transfers what's changed or missing.
So if you're syncing a massive on-prem archive to the cloud,
Or sync, -r is how you do it efficiently and cost-effectively. It minimizes unnecessary uploads.
and finally, applying those complex, high-stakes lifecycle and retention policies, the ones we define in JSON files, how do you push those to the bucket?
The lifecycle rules are always defined in a structured JSON file. You apply it with gsutil lifecycle set filename.json gs.bucket-name. And if you want to verify an object is locked under a retention policy, you use gsutil-else-l and check the metadata for the retention expiration time. That's how you prove it's worm compliance for an audit.
So what does this all mean? We've covered everything from fundamental global naming constraints to irreversible legal mandates.
Let's review the 4 strategic, high-value takeaways for anyone building or managing a modern cloud architecture.
First, solidify your bucket strategy.
Ditch the single bucket approach. Use multiple buckets to enforce distinct, specific policies for security, location, and storage class, tailored to every unique beta type you manage.
Second, make an intelligent location selection.
Match your location regional, dual region, or multi-region precisely to your application's latency needs, its user base, and its disaster recovery requirements. And always account for network egress costs.
Third, master your storage classes.
Match standard nearline, cold line, or archive to the data's access frequency. And never, ever violate those minimum duration periods without factoring in the early deletion fee.
And finally, leverage security and automation.
Use lifecycle management for automated cost reduction and compliance. Implement uniform bucket-level access for consistent, non-negotiable security via IAM. And use the locked retention policy only when worm compliance is a legal necessity.
We spent a lot of time on the irreversible nature of that locked retention policy, which brings us to our final thought.
It does. The guarantee it provides is absolute. Data cannot be deleted or overwritten for the period you set, say, 8 years, to satisfy some compliance rule.
It sounds like the ultimate guarantee of data integrity.
It is, but consider the hidden risk. On day 1, you accidentally write a terabyte of proprietary source code or highly sensitive client health records into that newly locked bucket.
Oh, no.
That retention policy ensures compliance, yes, but it also legally prevents you, the project owner, the CEO, anyone, from deleting that compromised data for the entire 8-year duration. You have just created an unchangeable legal record of a security breach.
You can't wipe the slate clean.
You cannot. The policy ensures compliance against deletion, but it forces you to have absolute trust in the integrity of the data you put there, because that worm contract is enforced no matter what. Good, bad, or catastrophic. That is the true weight of permanence in cloud architecture.
A truly write once, read many commitment that transcends human control. That's a powerful final thought for you to chew on as you architect your next storage solution.